In this section, we want to discuss some properties of the line integral. First, it is good to know that line integral of a vector field is actually a direct generalization of the definite integral of one function of one argument. Here, f arrow may be a vector field, a vector function, and dr is the element of all the independent variables. The arrow stands for vector in any dimensional space. 2-dimensional, no problem. 3-dimensional, no problem. 77 dimension, no problem. But dimension 1, no problem either. If the dimension is 1, then we don't have to write arrow, and we would write it as f x dx. While we were talking about the definite integral, we used the letter small f for the integrated function, and then we used capital F for the antiderivative. So don't be confused. This is not antiderivative. This is not the indefinite integral. This is the integrated function. Well, and here is the curve C, which in a one-dimensional case is just an interval. We usually write it from A to B. And if A is less than B, we can denote capital I, the interval from A to B. So this was the notation in the first semester for the definite integral. The lower limit, the upper limit, the starting value, the end value of the independent variable x. If we want to write it in the sense of the line integral, we would denote the AB interval by some single letter, and we would write the name of the integration interval beneath the integral sign. So what about some properties? If we have two vector fields, f arrow and t arrow, we can multiply each of them by some scalar constant, alpha and beta, and we can add these two results, and this bracket is a new vector field. Well, and then the line integral of this linear combination of these two vector fields is just the linear combination of the integrals of individual vector fields. Similarly, if we have two curves, C1 and C2, and when the endpoint of the first curve coincides with the initial point of the second curve, say this will be the curve C1, and this will be the curve C2. If the endpoint of C1 is the same as the initial point of C2, we can concatenate these two curves and we can build a new, longer curve. And this concatenation is denoted with plus, but we write a little dot to distinguish from plus that we use for adding numbers or vectors or matrices. If C1 and C2 are two smooth curves, that means the parameterization can be written using function that is continuous and has continuous derivatives and has non-zero derivatives. Then the resulting curve is not necessarily smooth again, as is illustrated by this example. Such a curve that is smooth up to a finite number of points is called piecewise smooth curve. And we can consider a line integral not just over a smooth curve, but a piecewise smooth curve, which is a generalization. And then, if we have some curve C with this orientation, and we evaluate the line integral, then if we consider the same curve but in the opposite, with the opposite orientation, which we denote minus c, then the line integral over this reversed curve is equal to the original integral with minus sign. This is easy to imagine if you apply some force. Say, if you take some object and you lift it up, you do some mechanical work. And if you go backwards, you can consume this work. So you do a negative work. That means if you are clever enough, you can consume, you can make use of this work, this difference of energy. So if we reverse the orientation of the curve, the integral changes the sign. This is a similar situation as for integral of scalar function. If we change the orientation, that means we don't go from A to B, but from B to A. And again, the result changes the sign. And actually, we can illustrate this again using definite integral of a scalar function, because if we concatenate two intervals, then the sum of the integrals is equal to the integral over this concatenation, namely integral from A to B plus integral from B to C is equal to integral from A to C for the same integrated function. You see here f must be the same. So these properties can be used to evaluate integral.